Hi everyone. Today we are jumping into section 9.4 and 9.5. So we're actually doing hypothesis tests. This one says for one population mean when sigma is known. 9.5 is just when sigma is unknown. But hypothesis tests, now we're actually doing the test. We talked in previous sections 9.1 through 9.3 about what the tests are, how to set them up, how to interpret. This is just going to be examples of actually doing the tests. So this is our first real step into what we're going to be doing the rest of the semester, hypothesis testing. So do get familiar with this. You're going to see a lot of it. Okay, so first of all, notice here, what we're trying to do is we're trying to test the population mean. And so we're just answering some question about the population mean and determining if we think the statement they give us is true or not. So we're testing the population mean mu. Okay, so what we're going to be doing is it's going to be very similar to what we did with the Z confidence interval. So you'll notice these are the same assumptions. So the assumptions for and we're doing a Z test. We'll talk about why it's a Z test in a minute, but very similar to what we did for a Z interval when we're testing a single population mean. So here's the assumptions. The first one still has to be a simple random sample. Second one, we still have to have either a normal population for our variable or a large sample size. We usually define a large sample size to be n is greater than or equal to 30. And then lastly, sigma, which is the population standard deviation, to be a Z test, we have to know what that is. So sigma is known. Those are our three assumptions. If those are all met, we can do a Z test and have comfort and confidence in our results. Okay. So let's talk about the steps for a hypothesis test. And I'm doing what they refer to as the p-value method. So there's different steps. Some of these steps change if we're doing what's called the critical value approach. This is the p-value approach. So steps for hypothesis test. First one, we have to state our hypotheses. And that's what we talked about last time. That's the null hypothesis, H sub 0, and the alternative hypothesis, H sub A. Remember, some authors will call that H sub 1 for the alternative. Our author calls it H sub A, so we'll stick with that. 2, determine what they refer to as the significance level. We call that alpha. And remember, that represents actually the probability that we're going to make a type 1 error or reject a null hypothesis that was actually true. That's usually set at 5%. But if we want to be extra careful about not making a type 1 error, we may make it lower. I've typically seen significance level alpha between about 1% and 5%. That will typically be given to us in the problem. All right, so our third step, now that we have that, what we're going to do, we need to select and run appropriate test. And our goal there is to find the p-value. Once we have the p-value, step 4 is we make decision about the null hypothesis H sub 0. And here's what I mean by that. Here's our decision. what we said before. If the p-value is less than or equal to the significance level alpha, reject H sub O, the null hypothesis. Otherwise, do not reject H sub O. But notice, either way, we state the decision in terms of the null hypothesis. Either reject the null hypothesis or we do not reject the null hypothesis. Again, some authors will say fail to reject the null hypothesis, meaning the same as do not reject the null hypothesis. And then lastly, we're going to state our conclusion, which is usually answering the question. Let's make that conclusion look a little bit better. So answer the question. And this one is in terms of the alternative hypothesis, H sub A. Okay, so the decision's based in terms of H sub 0, the null hypothesis. The conclusion is in terms of the alternative hypothesis, H sub A. The alternative hypothesis is typically the question that's being asked. Okay, so with that, I'm just going to run into some problems. We will figure these out, but let me show you, let's go through just something that the author tells us that he wants us to pay attention to as to whether or not we can actually do this z-test. So we'll go through this fairly quickly, but I wanted to post it for you. So it says, when to use the one mean z-test. Small samples, say less than 15. The z-test should be used only when the variable under consideration is normally distributed or very close to. So if you have a really small sample, we want the distribution to be normally distributed or very close. Moderate size samples between 15 and 30. The z-test can be used unless the data contains outliers or the variable under consideration is far from being normally distributed. And then for large samples of 30 or more, the z-test can be used essentially without restriction. So if there's outliers present and we can't justify the removal because it was a mistaken calculation or the way we recorded it was wrong, or there's something that we think that number shouldn't be in there, you should perform the hypothesis test once the outliers, once with the outliers and once without the outliers to see what effect the outliers have. If the conclusion's affected, use a different procedure or take another sample if possible. So you run it twice, once with and without the outlier in there. If you come to the same conclusion, then you're fine with your conclusion. If you come to different conclusions, then you may want to take another sample or run a different test. And if outliers are present, but their removal is justified and results in a data set for which the z-test is appropriate, then go ahead and use the z-test. Okay, so that kind of relates it based on sample size. Remember, the basis is very small sample, 15 or less. If you don't have a normally distributed variable, you don't want to run the z-test. If it's moderate between 15 and 30, then you can run it as long as it's pretty close to normally distributed and you don't have outliers. But if it's 30 or more, we remember from what we did before, we can run the test because all of the samples of size 30 or more would be normally distributed regardless of the shape of the underlying population. Okay, so let's do some tests. I'm just going to jump into my lab so that we can see how to do this. So let's look at problem 11. We'll pull that up. And we'll go through the hypothesis test steps. So it says the sample mean, sample size, and population standard deviation are provided below. Use the one mean z-test to perform the required hypothesis test at the 1% significance level. Now, we're going to assume we can run it. They don't tell us it's a simple random sample, but they told us to use the one mean z-test, so we assume that it is a simple random sample. It has to be normally distributed, which it doesn't say, or the sample size has to be large, 30 or more. Oh, the sample size 35, so we're okay. And then lastly, we need to know what the population standard deviation is, sigma, and they told us sigma 6. So we have the assumptions. So we can just go through and actually start working out the problem. Okay, so here's what we're going to do. We're going to run through this. So we've met the assumptions. Let's go through the steps. First, state the null and alternative hypotheses. They told us the null hypothesis mu is 29. So what they're saying is, okay, we're going to assume mu is 29, but what we really want to know is the alternative. Is mu really less than 29? So the question would be asking here, hey, is the mean less than 29? So we assume in the null hypothesis that it's not, and the alternative will say, well, if the evidence shows that the null hypothesis isn't true, then we'll go with the alternative. Second step, determine the significance level. They told us it's 1%. So alpha 0.01. Okay. Third step, what test? Well, since it met all the assumptions, I can run a z-test, which I'm going to do. And then what I want to find is the p-value. I'm going to find a couple things. I'm going to find the value of z, and I'm going to find the p-value. And the p-value calculation they give us came from the value of z. We're not actually physically going to use z because we're doing the p-value approach. If we were using the critical value approach, we'd use z specifically, but now we're just using the p-value. Again, it comes from z. It's just behind the scenes. We don't see it physically. So here's what I'm going to do. I'm going to leave that up there. Hopefully we can see things when I pull up StatCrunch. But I'm going to pull up StatCrunch and do this problem. So let's do this. So I'm going to go in, I'm going to go to question help and pull up StatCrunch. Okay, so I go into stat, z stats, one sample, because I'm doing a z test, one sample. There's only one sample that I'm doing here. One population is being tested, and I have the summary. I don't have all the individual data pieces. They told me what X bar were, etc. And so I'm going to go there. I'm going to pull that out. I need the mean, the standard deviation, and the sample size. So I'm going to go back real quickly since I can't see it from this page. And I'm going to pull back what they gave me for those numbers. So let's see. So they're telling me the mean, X bar, the sample mean is 25. So let's go back, put all these in. I've got n is 35. I've got sigma 6. Those are the only values I need. Let's go back in. So the sample mean, 25. The standard deviation was 6. And the sample size was 35. I'm doing a hypothesis test. Let's move this over so you can see a little bit better. I'm doing a hypothesis test this time. Remember last time confidence intervals, I checked the other bubble. Hypothesis test, the null mu equals, notice you can't change equals because there's always an equal in the null hypothesis. Well, in our case, 29. The alternative is that it's less than 29. And notice when I put 29 in here, we can't change the 29. Those are always the same number. So I've got a mu equals 29 is the null, and the alternative mu is less than 29. So now we just go to compute. Two numbers I'm going to get from this. One is the z value, one is the p value. And notice it's a really tiny p value. It's telling you it's less than 0.0001, meaning the 4 decimals, it's 0 because it's less than 0.0001. So when I write this, my z value, let's sketch this so I can put in my answers, negative 3.9440. I think they asked to 3 decimal places. I'm going to the 4th, so I know whether or not to round. Well, I guess I could have put this here. 3.9440. P-value, now they say less than 0.0001, so I'm going to say it's 0.0000. To 4 decimals, they say it that way because they want to say, hey, it's not 0 if you go out enough decimals. I don't want you to think that there's 0 chance because there's never 0 chance because the tails go off to infinity. But to 4 decimals, it rounds to 0. So that's my p-value. So now when I go in and I answer the questions, I've got everything I need. All right, so back to the problem. The test statistic z, they say 2 decimal places, so negative 3.94. All right, so we got that right. The p-value, I'm just going to put in 0. It says round to 3 decimals. All right, 0. All right. And notice I didn't have to put 0.000, but that's fine. All right, now let's state the conclusion. So here's what we do. I'm going to erase this part since we don't need it. But here's how we come to our conclusion. We look at this p-value down here. We say, look, this p-value is less than or equal to the 0.01, which was my alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis. That was my step 4. Well, that's the conclusion in terms of the null hypothesis. I reject it. I don't think that's true. So I state my conclusion in terms of the alternative. And I would say something along the way, it appears, the way I like to word it, we'll word it their way as well. It appears that mu is less than 29. Now they're going to be more formal. They're going to say, oh, the data provides sufficient evidence to say that mu is less than 29. But if we throw away the null hypothesis that mu is equal to 29, we have to go with the alternative, whatever the alternative was. And the alternative was less. And so that's how we state our answer. Let's see how they do it here. They're going to say, reject the null hypothesis. The data provides sufficient evidence to conclude that the mean is less than 29. And there's my conclusion. We'll get rid of all this so you can see it. And we'll check our answer. And yay, we get the right answer. Okay, so that's it. Let's do another example where we actually have the data. So let's go to another problem. And I'm going to go to problem 13. All right, it says cadmium, a heavy metal, is toxic to animals. Mushrooms, however, are able to absorb and accumulate cadmium at high concentrations. A government set a safety limit for cadmium in dry vegetables at 0.5 parts per million. The cadmium levels in a random sample of one species of edible mushroom are in the accompanying data set. At the 10% significance level, do the data provide sufficient evidence to conclude that the mean cadmium level in this species of mushrooms is greater than the government's recommended limit of 0.5 parts per million? Assume that the population standard deviation of cadmium levels in this species of mushrooms is 0.44 parts per million. And preliminary data analyses indicate that applying the z-test is reasonable. So it met all three of the assumptions we had to make. And then it says, note the sum of the data in case we don't have a computer to calculate the p-value. They're doing some of the work for us to save us a step. We don't need that. But let's go through the steps of the hypothesis test. 1, state your assumptions. So the null hypothesis and the alternative hypothesis. Well, they're asking us here, here's the question. Do the data provide sufficient evidence to conclude that the mean cadmium level in this species of mushroom is greater than the government's recommended limit of 0.5 parts per million? So we assume that no, it's equal to 0.5 parts per million. And the alternative is what the question's asking. Do we think it's greater? So we say, oh, let's check, let's test to see if mu is greater than 0.5 parts per million. So there's my null and alternative hypotheses. Then we go to step 2, we'll number that with 1. 2, significance level. Oh, this time they say alpha is 10% or 0.10. All right. Now, the test, they said it's appropriate to do z-test, so we're going to do a z-test. We're going to find the z-value, and we're going to find the p-value. So let's do it. All right, so let's see. What do I need here? A couple things I need. I know the 0.5, that was my null hypothesis. And sigma was 0.44. So that the sigma level, notice they gave me here, that was my population standard deviation. Okay, so we know that. So we have those values, so I can put those in. So now what I do is I go back to StatCrunch. I guess I could state my hypotheses first. So they say the null mu is equal to 0.5. mu is equal, remember, always an equal for the null, 0.5. The alternative, what we're testing, is greater than 0.5. All right, so we're good there. Compute the z value. Okay, let's run the test. Remember, I go StatCrunch. Yes, that was question help, StatCrunch. Got a lot of stuff there I don't need. Let's erase some of this. All right, so stat, zstat, one sample. This time I have the data. I opened it in the wrong spot. Let's close this down. That was silly of me. I need the data. So I click on the data and says, oh, there's the data. Now I'll open that in StatCrunch. So if I want the data populated for me, it'll do that for me. So there's all my data. Now I go into stat, zstat, one sample with data this time. Where's my data? Oh, it's in variable 1. So I click there. What's the standard deviation? Well, the standard deviation was 0.44. And a hypothesis test. Let me move this over so we can see it a little bit better. Hypothesis test. What was mu? Oh, it was 0.5 versus mu is greater than 0.5. So now I just go ahead and compute, and it gives me the z value and the p value. So my z value this time, 0.905. My p value, 0.1826. All right, let's enter those in. So now I go back. Let's shut that down. Don't need that. Okay, z value to 2 decimals. Well, that's going to be 0.91. Got that. What's the p value to 3 decimals? 0.183. Got that right? Okay, let's talk about the conclusion again. So here's what I do, and here's how I write it. The p value, 0.1826, remember, less than or equal to 0.10, which was alpha. That's what I'm comparing, the p value and alpha. But this time, it's not less than or equal to. What I do is I say, oh, wait, that's not less than or equal to. So I do not reject the null hypothesis. I like to think of it, is it less than or equal to? If yes, reject. If not, then don't reject. So to me, I don't have to memorize, oh, if it's less, do this. If it's greater, do that. I'm just thinking, hey, if it's less, I do this. If it's not, I do the opposite. That to me is easier. So you're never going to see me write that as greater than. I'm just going to say, look, it's not less than or equal to. So I do not reject the null hypothesis. And then my conclusion, if I can't reject this, then I have to say, no, the data is not sufficient or does not provide enough evidence to say that mu is actually greater than 0.05. So now when I state my conclusion in terms of the alternative, I say, no, the data does not provide sufficient evidence. To say what the alternative was, that mu actually is greater than 0.5 parts per million. And so notice my conclusion is still in terms of the alternative hypothesis, not in terms of the null hypothesis, but in terms of the alternative. And what's happening here, I can't say, oh, I don't reject it, so yes, mu is equal to 0.5. We don't think mu is equal to 0.5 because in our sample, we didn't get 0.5. We got a different number. We never calculated what it actually was, but it wasn't 0.5. But we say, was that sampling error too far to say that it couldn't be? Well, here we're saying, you know what? I don't have sufficient evidence to say that mu is greater than 0.5. Might it be? Yeah, it might. but there's an 18.26% chance that I would get these sample values if the null hypothesis are true. And that's not so unlikely that I don't think the null hypothesis could be true. I say, you know what? Null hypothesis might be true. So in this case, when I answer it, I say, do not reject the null hypothesis. At the 10% significance level, the data do not provide sufficient evidence to conclude that the mean cadmium level is more than the government's recommended limit. So notice again, the conclusion is all in terms of the alternative. The decision in terms of the null, the conclusion in terms of the alternative. All right, so got that. What I'm going to do from there, obviously clear all this off. But let's go back. Let's see if I can just lower this down. I'm going to go back and answer. Well, we're going to go into the next section. So that was all section 9.4. Let's go into 9.5. Notice the title is almost identical. Hypothesis test for one population mean, but this time sigma is unknown. So again, when we go in here, assumptions, now this is going to be a t-test. Same assumptions. So we'll do them here. Simple random sample. Normal population or large sample size. But this time, sigma is unknown. That's the difference. So if it is, we use this t-test. Now, one thing I want to talk about with t-test, let's capitalize test. There's something that they call degrees of freedom that they may ask you on some of the homework problem, which we use to calculate the t-value if we weren't having the computer calculate it for us. But the degrees of freedom, they just use df for degrees of freedom. And in this case, it's just going to be the sample size minus 1. So if they ask you something about degrees of freedom here, it's the sample size minus 1. So if the sample size is 30, obviously the degrees of freedom would be 29, that sort of thing. All right, let's use that. We'll go into a problem because everything else is set up the same way. So this is going to be another problem out of there. And I tried to leave up the problem so we can just jump in. And look, we're good here. So it's going to be problem 17. Let's just open up 17, see where we're at. Okay, so here's the question. And then stuff. It says, suppose a study reported that the average person watched 4.94 hours of television per day. A random sample of 15 people gave the number of hours of television watched per day shown. At the 1% significance level, do the data provide sufficient evidence to conclude that the amount of television watched per day last year by the average person differed from the value reported in the study? Okay, they give us that note of X bar and S, the sample mean and the sample standard deviation. We're not going to use those because we have the data. So if I calculated the mean and the standard from that data, I'd still get those numbers, but I don't want to have to. But I want to show you again how to use it using the data rather than the summary statistics. So this problem you could do either way because we have both the data and the summary statistics. We will use the data. Now, again, why are we using a z-test this time? Or why aren't we using the z-test? We don't have the population standard deviation. We just have the sample standard deviation sigma. So the sample standard deviation S, excuse me. So we're going to use S to approximate the population standard deviation sigma, which is why we have to use T instead of Z. So remember, if we have sigma, the population standard deviation, use Z. Don't have sigma, use T. That's it. That's the big difference between the two. So we're going to use a t-test this time. So let's go through the steps. Null hypothesis. All right, where's the question? Do the data provide sufficient evidence to conclude that the amount of television watched per day last year by the average person differed from the value reported in the study? Well, the study was 4.94. So we have to assume it's still 4.94 hours. That's my null hypothesis. But the alternative is what the question asked. Does it appear to have differed? Well, differed is it not equal? Might be more, might be less, we don't know. Is it different? And a lot of times when we do a study, we're thinking, I wonder if things have changed. I don't know, let's check. So sometimes you'll be sampling something and say, you know what, I bet you these hours watched on TV have increased. Let's do a greater than and check to see if it's increased. Because if it decreased, you don't care. But in this case, we just want to know if it's different. Are people watching more TV now for one reason or another? Or maybe they're using less because they're on social media more. I don't know. Let's make a test, see if it went, see if it changed. Did it differ? So there's my null and alternative hypotheses. We'll go ahead and answer these questions. So again, the null is always an equals, 4.94 in this case. And the alternative, this time is a not equal, and it's the same 4.94. Remember, those are always going to be the same values. All right, now find the value of t. Now, once we get down here, we knew it had to be a t-test. They kind of gave it away. So it is a t-test. So let's run the test. I'm going to do it on the data. So we'll go here, open in StatCrunch. Now, when I do this stat, t-stats, one sample. This time I have the data. This time I'm not going to put in the standard deviation because I don't have the population standard deviation. The computer is going to calculate the sample standard deviation on its own because it has all the data. So hypothesis test. Let's again move this over so that I can see. I'm going to erase those things. Let's see, where's my eraser? There it is. So let's erase this. Okay. So hypothesis test, mu is equal to 4.94 versus mu is not equal to 4.94. Oh, it's already a not equal. And now I just compute. And it gives me the value. Notice I do have the mean, degrees of freedom. Oh, there was 15 data pieces. Look, 15 data pieces. How to get the degrees of freedom? Oh, 15 minus 1. Again, most of the time they're not going to ask you for that, but this time they did. Again, I'm going to write these things down. I forgot to write down my alpha value. We'll do that shortly. So let's see. We'll leave a spot for it. We did get the t value is negative 3.82. Let's do a couple decimals so that I don't round depending on how they're going to ask us this time. 8167. And then the p-value, 0.0019. All right. So let's check. So let's go over. We don't need this. We'll just lower that down. Okay. The test statistic, t is negative 3, so 2 decimal places, so 3.1, negative 3.17. Not 3.17. Isn't that what I got? Let's go look again. 2 decimal places. How in the world? Oh, I just missed the 8 completely. Okay, so you guys were probably looking at that just giggling like, oh, Professor Monty, you've lost it. Sorta. All right, negative 3.8167. Good heavens. All right. Now we'll go back. So negative 3.82. There we go. Works a lot better when you write down the correct numbers. And then the p-value, 0.3 decimal places, so 0.002. All right, we got that. So now they want the conclusion. Well, I didn't do the significance level before. Notice up here, it says the significance level is 1%. So alpha is 0.01. So I take this and I say, oh, my p-value less than or equal to 0.01, which is alpha. And this one is, because if I move the decimal 2 places, I get 0.19%. And if I move the decimal 2 places here, I get 1%. Clearly, that is less than or equal to. So what happens? It is less, the p-value is less than alpha, so I reject the null hypothesis. Well, what does that mean? Well, if I reject that, I go with the alternative. So now I say, I answer the question that says, do the data provide sufficient evidence to conclude that the amount of television watched per day last year by the average person differed from the value reported in the study? I say yes. It appears, or the data is sufficient to show, I'm just going to say it appears, because we'll state it more formally in the wording. It appears that what? That mu is not equal to 4.94. All right, and let's put it in the words of the problem. So what did I do? I reject the null hypothesis. The data provides sufficient evidence to conclude that the amount of television watched by the average person is different from the value reported in the study. And I get a fantastic, which just gives me all kinds of happy feelings. I'm very proud of myself. I actually put in the right numbers this time, so that's a plus. All right, so anyway, that's the idea. So that should get you started. You should be able to look at those and work through some of this. If I show you more examples, it's not going to help. It's going to be the same idea. You have to do it so you get comfortable with what means what goes next, what these different things mean. But stick with it. Remember, we're going to do hypothesis testing the rest of the semester. So don't just, kind of say, I don't need to do this. This isn't that important. This is the most important thing that we're learning now. We're going to use it the rest of the semester. All right. So don't get discouraged. Work hard. But remember, you can do this.